And one of the questions I've often heard when I've presented observation-oriented modeling is, how do you plan sample size for your analysis? So you have your study designed, you have your analysis picked up. Now, how do you go about planning your sample size for your study? Now, a related question is, how do you determine statistical power for the OM software? Now, with regard to that second question, the answer is, don't worry about it. Null hypothesis significance testing has been set aside with observation-oriented modeling. So that means we're setting aside statistical power, we're setting aside type 1, type 2, and type 3 error rates, because those are all in the context of NHST. And the goal of that is to estimate a population parameter from a sample statistic. And we're not doing that with OM. What we're trying to do in OM is explain the pattern that we're seeing within our data. And it's that explanatory theory that allows us to generalize beyond our particular sample or particular study. But nonetheless, we can still plan sample size in observation-oriented modeling, because one of the things that we can do is try to rule out at least one competing explanation, and that is physical chance. So we can set up our sample size with the hopes of at least ruling out physical chance as one explanation of our data. If we can rule out physical chance, then we can turn to a conceptually meaningful interpretation of the data. So to plan sample size in observational modeling, what we're going to do is follow the spirit of David Trafimo's a priori procedure, the APP. You can read a number of papers that he's published in recent years about the APP. It's a superior procedure, in my opinion, if you're working within the context of null hypothesis significance testing. Here's one particular paper from 2019. Now, with the APP, you're going to work with particular statistics that you're familiar with, like a z-test for means, independent samples t-test, and so forth. And then for each of those, you're going to use a particular equation. That's going to help you then to plan your sample size. So as you can see on the screen here, we have a setup for a z-score, or a z-test, I should say, for means. And we can see here, for example, suppose the researcher wishes to have a 95% probability of obtaining a sample mean that is within a quarter of a standard deviation of the population mean. Because the z-score that corresponds to 95% confidence interval is approximately 1.96. Equation 1, as you can see on the screen here, can be solved as follows. Now, in other words, the researcher will need to recruit 62 participants for this particular example. So you have a z-test for means, you go to this equation, and you plug and chug through to get your sample size that you need for the study. Now, the two key concepts that we're going to pull from this, again, we're working in the spirit of Trafimo's approach here. We're not going to follow it exactly. But two key concepts we're going to pull out are this closeness value and this closeness proportion. So again, to reiterate, the question that we're answering here, Trafimo is answering, is how many participants should I recruit to my study if I wish 95% of the sample means to fall within a quarter of the standard deviation of the population mean? So the closeness value here is the quarter of a standard deviation, and the closeness proportion is that 95%. The answer is worked out using the appropriate formula for the given statistic. Now, with observational modeling, reading from the screen here, the goal is not normally to estimate population parameters, but to advance, again, a causal understanding of some phenomenon. The PCC index, the percent correct classifications index, is the primary stat that we will rely upon with the OM software. Although this is important, visual interpretation of the data are really what are key. Now, the PCC indicates the number of observations that match a theoretically meaningful pattern. Now, a chance value, or C-value, can also be used to help rule out physical chance as a competing explanation of an observed data pattern, as I mentioned a few moments ago. Now, the chance value is derived by creating numerous haphazard patterns, random patterns basically, in the data, and comparing the observed pattern to these haphazard patterns. This procedure is essentially referred to as a randomization test. The question then is, how many participants should I recruit to my study if I wish 95% of the PCCs to fall within 5 percentage points of the mean of these haphazardly generated PCCs? Now, I can change the 95% there and choose a different value. I can also change the 5 percentage points. But this is just an example of the question that we're now asking and how it's distinct from the question from null hypothesis significance testing and Trafimo's original APP procedure. Now, again, these PCCs are derived by randomly shuffling existing data or by randomly generating their deep structures. These PCCs represent possible worlds where physical chance is the only explanation for patterns in the data. And we want to look at these possible worlds and show that the actual data that we have is just unlikely. It's just, you're not going to see that very frequently within this realm of physical chance. Working from an example, let's consider a two-group study with positive and negative feedback conditions. They're independent, and a single rating outcome variable. Let's say it ranges from 1 to 7. Now, the researcher expects higher ratings for the positive feedback group compared to the negative feedback group. And using traditional statistics, an independent samples t-test could be conducted, and the appropriate APP formula could be used to determine the sample size. Now, in OOM, we're going to use what's called an ordinal pattern analysis. And we're going to expect that if we were to compare ratings from pairs of individuals taken from those two groups, a large majority would reveal higher values for the positive group. Namely, we expect this P greater than N, positive greater than negative ordinal pattern for a majority of those person-to-person comparisons. Now, how many people should we include in this study to test this predicted ordinal pattern? We're going to follow 4 steps here. Step 1, we're going to set our closeness value and our closest proportion, and let's just choose 5% and 95% respectively here. Again, they're arbitrarily chosen. What is the sample size needed for 95% of the PCCs from a randomization test to fall within that plus or minus 5 percentage point range within the mean of those PCCs? Now we then start by arbitrarily choosing a sample size, and let's just start with 15 here for this example, 15 in each group rather, so a total of 30 individuals. Then we're going to generate a data set comprised of ratings from 1 to 7. We can create these ratings with distributional expectations and with an expected percentage of comparisons that will match the P greater than N pattern. So if we have a priori data, a pilot study, for example, we can set up the data having particular characteristics or features. But we can also create the ratings just randomly without any distributional or proportional expectations. So for simplicity, let's go with this latter approach. And here are some example generated cases here. So we have the group and the rating observations. Now step 4, we're going to run the OM analysis with the expected P greater than N pattern. So we're going to run that ordinal pattern analysis in the software, and we're going to examine the distribution of the PCCs from the randomization test. So here we see the distribution from that analysis. And you can see I have things highlighted in red here. And I'll just read from the slide again. A total of 346. You can see I've added up the numbers in red there, and those are just frequencies. Of the randomized PCCs fall within plus or minus 5% of the mean of the distribution. So again, these are PCC values that I have computed from the randomization test based on the made-up data, the contrived data that I created. Now with 1,000 PCCs here, I ran 1,000 iterations, created 1,000 of these values. That's only 34.6%, and that's far too low then compared to the desired 95%. Also notice that the range of the PCCs, with randomly generated and shuffled data, PCCs as high as 95 or 75%, I should say, are possible by physical chance alone. So when I've just randomly created the data and then randomly shuffled it and looked for that P greater than N pattern, I could find PCCs greater than 75%. That's a fairly high PCC index, but we're getting that just by randomly generating and shuffling data. So clearly there is a lot of potential then to find high PCCs that are just due to physical chance, not due to some causal process. Now also notice the mean of this distribution is not 50%, as you might expect, because ties in the ordinal pattern analysis are counted as incorrect classification. So you're going to get something less than 50% here because those ties are going to go into an incorrect classification. It's going to reduce that PCC by a little bit. Now let's try. So we just iterate through. We're going to try 50 people per group. So we create a random data set, run the ordinal pattern analysis, generate the 1,000 PCCs again from the randomization test. And here we see it's now up to 633 of the randomized PCCs fall within plus or minus 5 percentage points of the mean. And that's, again, with 1,000 PCCs, that's only 63.3%, so still too low compared to the 95%. So then I went ahead and bumped it up quite high to 200 per group, so 400 total. And now we get 926 rather of the randomization PCCs fall within that plus or minus 5 percentage points of the mean of this distribution. And so we're close to the 95%. Now we could just stop here or try a larger sample size. We want to get an inch close to that 95%, but it's really perhaps close enough at this point to the 95%. So we could just stop here, and this would be our planned sample size then, 200 per group, a total of 400 individuals. Now also notice what's happened here with the range. The range of the PCCs now is 34.49 up to 52.12. So that range has shrunk compared to when we only had 15 per group. So the values greater than even just 51% here are now quite unusual. So that distribution is really kind of tightened up around the mean. That indicates then finding high PCCs, like let's say 70% in our actual data, going to be very, very unusual. You can't just create that kind of PCC by randomly shuffling data. So that is the procedure then in a nutshell. It's a bit like a Monte Carlo simulation. You set up your closeness value and your closeness proportion, and then you work through the analysis until you arrive at the number of individuals who match up or create that distribution to match those values. Now, some benefits of this OOM-APP procedure. Again, it's the spirit of the APP procedure here. It forces you to think about your study design and analysis procedure up front and in ways that will help you to debug potential issues in your study. It will help to improve your study. Now, while not obvious in the example we just worked through, it forces you to really think about the measurement issue. Now, you must really be ready to give a defense of exactly what your numbers mean as you set up and test your causal patterns. Now, while the APP assumes random sampling, this assumption is not needed with the OOM-APP approach, so we can discard the random sampling assumption. And then lastly, the OOM-APP approach does not require equations, as it's adaptable to any data structure and predicted pattern that you can come up with. All you need to do is determine the analysis to be conducted, generate your hypothetical data, and then run the analysis over and over until you determine the sample size. Just keep going through the procedure as we did before until you get a sample size that matches those closeness values. Now, one closing comment here. The steps presented above are to be performed with the understanding that this is not an exact science, and it doesn't need to be an exact science. Tweaking the sample size in the steps above, for example, until the closeness percentage matches the desired target, let's say 0.01%, reveals that we're really not understanding how we should be thinking about data and analysis and theory in observational or modeling. Again, it's the theories, the patterns in the data, the PCC index itself, and exact replication, right, that far exceed the chance value, the C value in importance. So we don't want to obsess over that C value in the OM software. So again, the goal here is to determine a sample size that will aid us in our efforts to convince critics of the plausibility of our causal theory. And this OOM-APP procedure, or the steps, could be helpful in that endeavor. So it gives me a little more of a succinct technical answer to that question: how do you determine sample size in the OM software or from the OM approach?